Hey there, in this video I'm going to talk about stretching and compression. And by the way, I'm using this physics coursebook to teach this chapter. And this physics coursebook is suitable for GCSE students who are taking their final exams. If you have this physics coursebook, do go to page 64 and page 65. The chapter is stretching and compression. So let's say we have a spring. We have a black spring. I will use black color pens. We have black spring, okay, and the length of this spring is 5 mm. So a spring, we can stretch it, right? We can stretch a spring because it's elastic. So after we stretch it 5 mm, there will be an extension, right? We do not know what's the extension. We just put x there. It's an unknown. If we further stretch it, if we stretch this spring, which means we are adding a force, right? Maybe we apply a force here, we apply a force here, okay, and we apply a force here. And if we further stretch it, okay, this guy will be our new extension. Let's put, this is x1, let's put this as x2, okay. But when we stretch a spring, if we release it, it will go back to its own original position, right? Original length. That is why the spring is elastic. But do you realize that if you overstretch a spring like this spring here will not go back to its original position, okay? Which means it's permanently in this shape, permanently in this length. It will not go back to its original position. The reason is simple. This brings us to Hooke's law. This brings us to Hooke's law. Hooke's law. Okay, Hooke's law. So just let me take this on top to here. Okay, so the principle of Hooke's law from my course book, it's a material obeys Hooke's law if beneath its elastic limit. The extension is proportional to the load. Okay, so a material obeys Hooke's law if beneath means below its elastic limit, which is the extension is proportional to the load. So Hooke's law, it has a formula, it is F equals to K times X, which is F equals to Kx. The force here, the F here, we call it as load, or we can call it as, yeah, load, and the load is force is Newton, and times K is the spring constant, and times the spring's extension. So we'll call this as F equals to Kx. It's easier to memorize this formula in this way, F equals to Kx, instead of saying load equals to spring constant and extension. Okay, so right here, if we plot a graph here, that's why I use this template today. It's because I need to draw a graph to explain it. So in a graph, we have independent variable and dependent variable. So the independent variable is where it's independent, which means no one could control it. Let's say time. Notice that time is always in the x-axis. This is x and this is y. Because we can't control time, time is independent, okay? So in this case, the force is going to be the independent, the load. The reason is because no one could control how much force that we are going to apply in the spring or on the spring. And the dependent variable is going to be the extension, right? More force, more extension on the spring. So extension. Okay, and I'm just going to plot this graph, and let me draw a line here, a line, and I'm going to draw a spring. I need 3 results, so 1, 3, 1, 2, 3. Okay, so let's say, so let me just draw one line here. Okay. Okay. So this line tells us that the original length of this spring is going to be here to here, an unknown distance, okay, an unknown length. So let me just erase this real quick. Okay. So notice that this spring, it has extended, right? There is extension in this spring, and the extension is going to be 10 mm. The reason is because we add load in it. Let's say we add a metal block, which is 1 Newton. So the force pulling this spring is going to be 1 Newton as well. Okay, an arrow and red arrow here. So if you add more load in it, which is more force pulling, so let's say, so the extension here will be greater, right? It's because F equals to kx. If we increase in force, must increase in extension. This k right here is the constant of the spring, which is the gradient. So let me just erase this. I do not need this right here. Okay. So this is going to be 20 mm. And we have added 2 metal blocks, which is the total load of this, which is the total force pulling will be 2 newtons. Okay, so more force, more extension, lesser force, lesser extension. That's how the formula works. Okay, so let's plot this into a graph. Let's see how it looks. So I'm just going to start here with 0 and 1, 2, 3 and 4 and 10. Okay, 10, 20, 30, 40. Okay, just 40. And let me erase this. Let me just extend this graph a little bit. Okay, so 50, and this is our dependent variable. Okay, so if you plot this in, let's plot this. And another thing is that this graph, this Hooke's law graph, always starts from the 0, which means right here there is no extension. This is the original length of it. So 0 extension means 0, and because 0 extension means 0 load, so 0, 0 is right here. It's a mass. So start from 0, 0 and 1 Newton, which means 10 mm. Let's put this in mm. Okay, so 2 newtons, which means 20 mm. So if we further add it, we add more force in it, add more load in it. So if we further plot it, it will be like this. This graph is going to be like this. Okay, but slowly this graph is going to be, wait, just let me draw a line here first. Okay, oops. Okay, so if you further plot it, this graph is slowly like this. We have a curve. Okay, we have a curve maybe like this. Okay, we have a curve. So I'm just going to name this as point X, and this one, and the another point is the point E. Okay, point E and point X. So the point X, anything below point X, so anything below point X, it will obey the Hooke's law, which is F equals to Kx, okay? And furthermore, anything above point X is not going to obey F equals to Kx. No more Hooke's law, anything above the point X. And what's special about point E is that anything below point E, it will return to its own original length, okay? So in this zone, this blue zone, there is no F equals to Kx. Anything above point X, it will not obey the F equals to Kx. But this point E, even though it does not obey the Hooke's law, it does not obey the F equals to Kx, but it will still return to its own original length, which means the spring is going to return to its own original length, okay? So this name, I'm just going to call it of limit of proportionality, okay, which means the limit of F equals to Kx. And this point E, I'm going to name it as elastic limit, okay, which is the maximum point where it's going to return to its own original length, okay? So anything, and again, this red zone right here, it will obey the F equals to Kx, which is Hooke's law, okay? This blue zone, it does not obey F equals to Kx, but it will return to its own original length, okay? So that's it for this video. I hope you have understood what I had just explained. And by the way, do remember to subscribe to my channel to increase my channel's algorithm. And I will see you in the next one. Bye.